everyone, welcome to today's video on acids, bases and salts. The first question, why do we need to study about acids, bases and salts? I'll show you so many things around us that are actually acidic or basic or they are salt. In fact, all of these things are very useful in our day-to-day life. Talk about citrus fruits like oranges, lemon, lime, amla, they all have citric acid. The stomach acid, that is hydrochloric acid, play a very crucial role in the process of digestion, is again an acid. Most of the fertilizers are acidic in nature. Perfumes which are otherwise neutral, but if they have an ingredient like lime or lemon, they become acidic in nature. Not just acids, if we talk about bases, there are so many bases around us, starting from washing soda to baking soda, bleaching powder, toothpaste, antacids, they are all bases. Salts, needless to say, we have the common salt, which is like an essential ingredient in our cooking. So what are we waiting for? Let's get started and understand more about acids, bases and salts. In this video, we will learn about acids, bases and salts, acid-base indicators, reactions of acids and bases, strength of acids and bases, the concept of pH, and chemicals obtained from common salt. Watch the entire playlist to get the best explanation on acids, bases and salts. Let's get started. What is an acid? A solution that has an excess of hydrogen ions and are sour in taste. Think of the citrus fruits like sweet lime and lemon. They are sour in taste and they are acidic in nature because they have citric acid. What do we mean by excess of H plus ions? That actually means that acids dissociate in water to produce hydrogen ions. In fact, if you talk about a strong acid, it ionizes completely to produce hydrogen ions and negatively charged ions. Now, what it means is anything that has a lot of excess stock of hydrogen ions. Now, if it gets a chance to release some ions, let's say because of ionization or something, so what will it do? It will release the hydrogen ions, right? So that's exactly what is true with acid. They have excess of hydrogen ions and therefore they tend to release hydrogen ions in solution. Let us now quickly look at the history of acid, and I think it would be interesting to know about it. Well, people have been defining acids in many different ways since hundreds of years rather. So looking at this, you can see that there were scientists who were trying to define acids in 1700s till 1900s. So it's like so many years and people were just trying to figure out what exactly were acids. Long time ago, the Greek, they defined acid by taste. So they said that anything that tastes sour is acid, which is partially true today, but it is not like the basic definition of acid. A couple of years later, around 1776, Lavoisier told that acids should be defined by structure. So any structure that has oxygen is acid. But again, to his contrary, a few years later, Davy said that it was not on the basis of oxygen that we can define acid. However, Davy did not give any specific definition of acid, but all he did was he tried to tell that the definition that Lavoisier gave was incorrect because he found that there were some acids that did not have oxygen in their structure. Again, a few years later, Vaughan came up with a new definition of acid, and he said that one with hydrogen is acid. So he said that presence of hydrogen tells us about the acidic nature of a particular substance. Again, few years passed by, then came Arrhenius. He said that substances delivering hydrogen cations to the solution are acids. So he completely relied on water. So he said that if you have a substance which you have to identify whether it is acid or not, so you will have to dip that in water and see if it is releasing hydrogen ions. So his definition was completely on the basis of like water, like how does it behave in water. But his thought was that any such substance which releases hydrogen ions in water is acid. Now, later came up Albert F.O., who in a way supported Arrhenius' definition, but he tried to generalize the definition to cover aprotic solvent. Because Arrhenius' definition was very specific to water, like in water, if a substance behaves this way, it is acid. But Albert said that that doesn't work, right? So we need to take into consideration all the other type of solvents as well. So he kind of extended Arrhenius' definition to aprotic solvent. Now you may ask, what is aprotic solvent? Now solvents are of two categories. One is protic solvent, the other one is aprotic solvent. So protic means a solvent that contains hydrogen ions or protons. So that's why they are called protic solvent. And in exactly similar way, aprotic solvents are those which are without protons or without hydrogen atoms. Therefore, there are no oxygen hydrogen or nitrogen hydrogen bonds. So they are aprotic solvent. So obviously water falls under the category of protic solvent. So therefore Albert F.O. said that Arrhenius' definition is true, but this is true even for aprotic solvent. Okay. Finally, a few years later again, around 1923, Bronsted and Lowry, they said that ability of acids to donate hydrogen ions or protons to bases which accept them. So they said that yes, this is true, that substance that has a tendency to release hydrogen ions are acids, and these hydrogen ions in turn are accepted by some other set of substances and they are called bases. And today the definition that we learn is also on the same basis, that any substance that releases hydrogen ions or that has excess of hydrogen ions are acids. So if you look at this example, like when an acid reacts with a base, acid like hydrochloric acid, when it reacts with a base like sodium hydroxide, what happens? Hydrochloric acid tends to lose H plus ions, right? And then these H plus ions are accepted by the base, that is OH, and OH and H plus, they combine to form H2O. So left behind are Na and Cl, so they combine together to form the salt. So we very clearly see here that how acids lose hydrogen ions and how bases accept them. So this is how acids came into picture and they were defined. Acids are present in a wide variety of things around us, like vinegar, aspirin, vitamin C, soda water, soft drinks, citrus fruits, stomach acid, fertilizer, explosives, car batteries, and the list is too long, isn't it? So this lists some of the acids which are present in most of the common substances that we see around us, starting from vinegar to aspirin to soft drinks, soda water, in fact even the stomach acid which helps in the process of digestion, fertilizers, and even car batteries. There are so many different types of acids present in different forms and different objects around us that a classification of acid became necessary. Acids are classified into different types based on different factors. On the basis of origin, acids are of two types, organic acids and mineral acids. On the basis of strength, acids again are of two types, strong acids, weak acids. On the basis of concentration, they are again of two types, dilute acid and concentrated acid. And on the basis of state, acids are of three types, solid, liquid, and gas acids. Organic acids. Organic, anything that is derived from living organisms are generally called as organic. So these acids are also derived from living organisms like plants or animals. Now generally they are weak acids and therefore they are not harmful for living organisms. So examples of organic acids would be citric fruits. So citric acid is present in fruits like oranges, lemons, etc. Besides that, acetic acid in vinegar, oxalic acid in tomato, tartaric acid in tamarind, or lactic acid in milk or curd. So these are all examples of organic acids, because if you look at them, they are all derived from fruits, vegetables, milk products, and these are all like derived directly or indirectly from plants and animals. Now, they are weak acids, not at all harmful for living organisms. On the other hand, we have inorganic acids, which are also known as mineral acids. Now, they are quite strong, they are dangerous and corrosive as well. So, examples of such acids are hydrochloric acid, sulfuric acid. So, we normally use them in our chemistry laboratories, right, to perform different experiments. But these acids are very harmful for us, and therefore we do not consume them in any form. Let's see, what do we mean by strong and weak acids? So strong acids completely dissociate into its ions in aqueous solutions. Now this is important, completely dissociate. Some examples of strong acids are hydrochloric acid, sulfuric acid, nitric acid. So if you look at these acids, for example, if you talk about hydrochloric acid, this will completely dissociate to form H plus and Cl minus. And these ions which are formed, hydrogen ions or chloride ions, they do not recombine. So these are examples of strong acids. On the other hand, if you talk about weak acids, they do not completely dissociate. So they dissociate, but they dissociate partially into their ions in aqueous solutions. Some of the examples of weak acids are carbonic acid, acetic acid. So if you look at these examples, let us talk about acetic acid, CH3COOH. So they partially dissociate to form H plus and CH3COO minus. So do you see the symbol? This shows that it's not that it completely dissociates into these ions and they never recombine. It's not like that. So here this acid dissociate to form these ions, but these ions recombine to form the acid again. So what we notice is, in case of weak acids, only a small fraction of the molecules ionize to hydrogen ions and acetate ions, and most of it remain as unionized acetic acid molecules. So that's the major difference between strong acid and weak acids. Dilute and concentrated acids. Dilute means low concentration of acids in aqueous solution. That means, let's suppose, so just to remember what is dilute and which one is concentrated. Dilute means when you add lot of water to anything. So you would have heard that your mother or grandmother would scold the milkman for diluting the milk with a lot of water. So when you mix a lot of water into something, that becomes the dilute version. Similarly, when you have less acid and more water, that's dilute acid. So the percentage of acid is less in case of dilute acids. But when you talk about concentrated acids, that means there is high concentration of acids in aqueous solution. So that's like more percentage of acid comparatively in the aqueous solution. Right, so that's the difference between dilute and concentrated. Now for most of these acids, you would have seen that for many reactions it is written dilute HCl. At some places it is written concentrated HCl. That actually means, dilute means you have mixed a lot of water with that hydrochloric acid. Concentrated means you just have that pure concentrated HCl, no water mixed to it. Right? So obviously concentrated hydrochloric acid is a lot more dangerous than dilute hydrochloric acid. Just like how we have 3 states of matter, in a similar way we also classify acids into 3 types based on their state. That is solid acids, liquid acids and gaseous acid. So solid acids examples are HiO3 and sulfanilic acid. Liquid acids are hydrochloric acid, sulfuric acid, and gas acids are carbon dioxide, H2S. So these are all examples of gas acids which are in gaseous form. So an interesting fact in this regard is hydrochloric acid. So what is hydrochloric acid? It is HCl. HCl is also hydrogen chloride, and hydrogen chloride is a gas. So hydrogen chloride is a gas. But hydrochloric acid is liquid. So how do we get hydrochloric acid from hydrogen chloride gas? So basically, when hydrogen chloride gas is dissolved in water, we get hydrochloric acid, which is liquid, which is in the liquid form. So this is when we get H3O plus Cl minus, and from here we get hydrochloric acid, which is in liquid form. What is a base? Bitter in taste and soapy in touch. Now, that doesn't mean that you go and try to taste a base, because that could be extremely poisonous for your health. So do not attempt to do that. Just trust me that bases are bitter in taste. Now, as far as defining a base is concerned, there are two definitions. The old definition says that a solution that has an excess of hydroxide ions is a base. The new definition says that an object that accepts the hydrogen ions is a base. Now, both of these definitions are correct, but if you go to their accuracy, the old definition is correct for 99% of the cases, while the new definition is correct for 100% of the cases. So let's take a look how. Two examples of bases, that is NaOH and NH3. Both of these are bases, and with these two examples we will try to see that the new definition holds true for most of the cases. So let's look at the first case, that is sodium hydroxide, NaOH. So here we see this has excess of OH minus ions, so we can actually see that it has OH minus ions. So that way the old definition is true. We also see that NaOH takes H plus ions to form H2O. So it also accepts H plus ions. How do we know that? When NaOH reacts with HCl, hydrochloric acid, what happens? Hydrochloric acid releases H plus ions, and this OH, it accepts H plus ions and it forms NaCl plus H2O. So basically it accepts the hydrogen ions to form water. So that means the new definition is also true. Now let us look at the second example, that is NH3, ammonia. Now this is a base, but if we look at the old definition, does it have OH minus ions? No. So the old definition is not true in this case. But as per the new definition, does NH3 accepts hydrogen ions? Yes, it does. Let us look at this reaction. What happens when NH3 reacts with HCl? Now HCl again tends to release the H plus ions, and who accepts that? NH3, and it forms NH4Cl. Right? So we see that in this case, even though NH3 doesn't have OH minus ions, but it still accepts the hydrogen ions released by acid. Correct? So that means the new definition is correct. So both of these are bases. In the first case, both old and new definition are true. In the second case, only the new definition is true. So that is why we consider that the new definition is more generic, because it is true in 100% of the cases, but the old definition is true only in 99% of the cases. List some of the common bases which are present in things around us, starting from antacids to deodorants to glass cleaner to the plaster of Paris, laxatives, or even if you talk about very common things which we normally use for baking, like baking soda or dish detergent or drain cleaner or even bleach. So these are names of some of those common bases, and I think it will be good if you know these names, like which are the bases present in each of these things around us. Just like acids, bases are also of different types based on different factors. On the basis of strength, they are of two types: strong base, weak base. On the basis of concentration, they are again of two types: dilute base, concentrated base. On the basis of state, they are of three types: solid, liquid, and gas. Strong base and weak base. So just like strong acids and weak acids, strong base, they completely dissociate into its ions in aqueous solution. So whether it is a strong base or a strong acid, they completely dissociate. So examples of strong bases are sodium hydroxide, potassium hydroxide. So if you look at these, so NaOH, so they completely dissociate to form Na plus and OH minus ions. On the other hand, if you talk about weak bases, they do not completely dissociate. into their ions. Let's look at examples like NH4OH, ammonium hydroxide. So NH4OH, they dissociate but partly dissociate to form NH4 plus OH minus ions. This means that these ions formed, they tend to recombine to form NH4OH. So overall, only a small fraction of NH4OH dissociate into NH4 plus and OH minus. Most of it remain as NH4OH. Right? So that's about strong and weak bases. Let's talk about dilute bases and concentrated bases. So dilute bases, again, low concentration of alkali, that is the base, in aqueous solutions. So exactly, the concept is exactly the same as in dilute and concentrated acids. So examples of dilute bases could be any base which is in the dilute form, like lot of water has been added to it. Concentrated means high concentration of alkali in aqueous solution. So for example, if you say dilute NaOH, that would actually mean that a lot of water has been added to it. Therefore, the actual concentration of NaOH is very less. So that's dilute. And if you say concentrated NaOH, that means there is no water that has been added to it. Let's also talk about solid, liquid and gas forms of bases. So examples are sodium hydroxide, which is in the solid form, as you can see in this in the picture. They are in the form of these white color crystals. Then you have the liquid form, which is like water, like that's the form. And then you have gas, NH3, ammonia. It is in the gas form, but this is also a base. What is a salt? Not always common salt that we use for cooking. In fact, there are a lot of other salts. In fact, we have a family of salts that are extremely useful for us in some way or the other. Salts are actually ionic compounds which are a result of neutralization reaction between an acid and a base. So let's look at it. Examples of salts. Common salt, of course, which is widely used in cooking and also used as a preservative. You must have observed that a lot of salt is generally put when you prepare a pickle. Can you think of other examples of salts? Like potassium permanganate, which is used to treat a lot of skin infections. Potassium dichromate is another example of salt. In fact, we'll talk about a lot of salts in more detail just now. A quick question that might come to many of your mind: why is common salt called common salt when we have so many other salts? That's because this is one of the most commonly used salt which we use in our day-to-day life, and that's why we call it common salt. So common salt chemically is sodium chloride, NaCl. Salts exist in many different colors. For example, if you talk about sodium chromate, it's yellow, potassium dichromate orange, potassium ferricyanide red, and you can actually see so many multiple colors starting from yellow, orange, red, mauve, blue, purple, green, white, or even colorless like magnesium sulfate, heptahydrate. So these are examples of some salts with their respective colors, just to give you an idea that salts are not of any specific color. A lot of us just think about sodium chloride, that is common salt, which we use in our cooking and for eating purposes. So salt means it's always like sodium chloride, but that's not the case. There are so many other types of salts which are available in so many different colors. I hope you found this video on introduction of acids, bases and salts useful. In the next video, we are going to talk about acid-base indicators. So stay tuned.